The first type of nomenclature that we're going to look at is Ionic Compound Nomenclature. Note that this information is found in section 6.2 to 6.4 of the Chem 2A textbook and in section 5.5 to 5.7 of the Chem 22 textbook. The two major rules that you have to keep in mind, first and foremost, when you are doing ionic compound nomenclature, is that you will either name or write the chemical symbol for the metal cation first, followed by the non-metal anion, named or written last. That's rule 1, and rule 2, total charges on all ions must add up to 0. In order for a compound to be stable, it has to be electrically neutral overall. And note, and I'll be mentioning this repeatedly as I work with you individually on nomenclature, you will not be successful in naming compounds if you have not memorized the table of ion names and formulas that's found in the end of your lab manual. So this is a very important process that you must put into your mind, having the names and formulas of these ions. And I'm holding up here the Chem 22 table of ions found at the end of the lab manual. You need to continue to work on memorizing, practicing these names and formulas throughout the course. Okay, so let's take a look at how we do name metal cations and then non-metal anions in closer detail. Metal cations, they take the name of the element they come from. If there are multiple charges possible, as would be the case with transition metals, then you're going to need to include an extra step by indicating the charge on the ion using a Roman numeral in parentheses. And we're going to illustrate these with some examples below. So our group 1A and group 2A cations, our alkali metal and alkaline earth metal families. We know that they will lose electrons and form a positively charged cation, and group 1A metals will always be +1 charge in ionic compounds. Group 2A metals always +2 in ionic compounds as cations. So you can just predict these using the periodic table. Example, sodium +1, Na+1. You name it by simply naming the element, the sodium ion. Potassium +1, K+1, the potassium ion. Mg+2, the magnesium ion. We're just taking the name of the element in naming the ion. And Ca+2, the calcium ion. And of course, our group 1 cations with a +1 charge, our group 2 cations with a +2 charge. The situation is a little more complex with transition metal cations. They usually have more than one charge state possible, and that's the direct result of the influence of their d electrons. So we would anticipate that there is more than one possible charge available for transition metals, except in the case of silver and zinc. Silver is always a +1 cation. Zinc is always a +2 cation in compounds, so you would not include Roman numerals when you name these compounds. And if you glance right now at your table of ions and look at each of these two cations, you will see that no Roman numeral is included in their name. It is simply the silver ion, and you have to memorize that it has a +1 charge, or the zinc ion, no Roman numeral, and you have to memorize that zinc has a +2 charge always in ionic compounds. But most of the transition metals have more than one possible positive charge state available to them. And let's examine two very common types of transition metals and the charges that are possible for them. If you look on your ion table sheet, you will see that iron is listed as both a +2 ion and a +3 ion. And you name iron by giving the name of the element and then indicating the charge on the ion with a Roman numeral in parentheses. So Fe plus 2 would be called the iron plus 2 ion. Fe plus 3 would be the iron 3 ion, using the Roman numeral in parentheses. But you see here on the sheet and also on my board that there is an alternate name that is possible for iron 2 and iron 3. This is an older naming system that is no longer the preferred way to name these cations. So notice the asterisk means this is what I would want you to personally use and adopt as your system for naming these cations. Fe plus 2, I'd prefer that you call it the iron 2 ion. Fe plus 3, the iron 3 cation. But I want you to recognize this older system of nomenclature because you may encounter it either in your reading in the lab manual or in the lab itself on a label or in literature or in other places that you may pursue as you go further in your science study. So the iron 2 ion can also be referred to as the ferrous ion, the older method. The iron 3 ion can be referred to as the ferric ion. And notice that I've highlighted the suffixes for each of these ions. The us refers to the ion with lower charge, the ic, the ion with higher charge. And it's immediately obvious what is less advantageous about this system. For reading the name of the ferrous ion doesn't immediately indicate that the charge on the iron is plus 2. You would have already had to memorize that iron can be in either a plus 2 or a plus 3 state, and the us suffix correlates with the ion of lower positive charge. The ic suffix with the ion of higher positive charge. Illustrating this system again with the copper 1 and the copper 2 cations. So the preferred naming system is to write the name of the element and put the charge on the ion using a Roman numeral in parentheses. So copper 1 ion, copper 2 ion, Cu plus 2. But there is this older system that you may be asked to recognize where you use the suffixes us and ic, the us suffix correlating to the lower charge ion, so copper 1 would be the cuprous ion, and the plus 2 would be called cupric with the ic suffix. And you also may be wondering why these strange fer prefixes, cup prefixes. I should have mentioned that the beginning part of the name comes from either the Latin or the Greek name for the element. So iron is known as ferrum, either Latin or Greek name, and copper is known as cuprum, either Latin or Greek. So we can clearly see why this older system is not nearly as convenient, but still something that you may see and encounter and be asked to recognize. So you are responsible for understanding these older names for these ions, and they are listed on your table of ion names and formulas that you are responsible for memorizing. Let's transition now to take a look at naming the anions, the nonmetal anions. If you look at the right side of your table of ions, you'll see that the right side lists the anions, the left side the cations. Examining the right side anions and looking at the names of these ions, you will see that they have a suffix ending of either "ide" or "ite" or "ate." So let's help you decode what that means. If the anion ends in "ide," that's an indication to you that you are looking at a monatomic anion, a single atom anion. So for example, fluorine, when it becomes an anion, gains an electron. Group 7A, 7 valence electrons, needs to gain 1 electron to have an octet. So we see fluorine forming a -1 anion. The same reasoning applies to chlorine and then all the members of the halogen family. Once fluorine and the rest of the halogens becomes a negatively charged anion, they undergo a name change. We drop off the ending of the name of the element and add the suffix IDE. So if you look at the name of an anion and see that it ends in IDE, that is a big clue to you that you are looking at a monatomic anion, single atom anion. So examples here: fluoride, F-1, chloride, Cl-1. Oxygen in family 6A would gain 2 electrons to achieve an octet, and when it becomes a -2 anion, its name changes to oxide. Nitrogen in family 5A would gain 3 electrons to achieve an octet, and once it is a -3 anion, its name is now nitride. So you see how all these monatomic anions end in the suffix IDE. But of course, it's the exceptions that always trip us up. And if you examine the table, you will see 3 polyatomic anions that regrettably also end in IDE. I think these ions were named prior to scientists sitting down and saying, let's get systematic about this. And these older names were so widespread in use that they just stuck. So unfortunately, the 3 ions that I have listed here are all polyatomic ions, not monatomic anions, but polyatomic anions, and regrettably, their names also end in IDE. So looking at this, we see Cn-1, the cyanide ion, OH-1, the hydroxide ion, and O2-2 peroxide anion. All of these are polyatomic anions, but their names do also end in IDE, which is an exception to the overall principle that monatomic anions, single atom anions, end in IDE. Let's take a look at 2 other categories of polyatomic anions whose names we see listed on the sheet as well as their formulas. If you look at these, you will see that these anions either end in the suffix "ite" or the suffix "ate." If you see that the anion ends in "ite" or "ate," what you should anticipate is that typically these are oxyanions. Oxyanions are anions formed by a nonmetal atom in combination with 1 or more oxygen atoms. So looking at polyatomic anions ending in "ate," and you may wonder why I am starting with the polyatomic anions ending in "ate. The reason that I'm starting with them is that I'm suggesting that these are the anions that you memorize, and many of them have a counter anion that ends in "ite," and it will be very easy to figure out the charge on the counter anion "ite" if you have memorized the formula and charge of their "ate" companion. So, for example, if you look at your table, you'll see NO3-1, the nitrate anion. Now, if you memorize the nitrate anion, you can immediately figure out the formula of its companion nitrite anion, which has the formula NO2 minus 1. And what you see is that the charge on these pair of ions stays the same, but you subtract one oxygen in the ite form of the anion. So nitrite has one less oxygen atom in its formula than nitrate, but has the same charge of minus 1. And we see that pattern carried out with these other oxyanions. Sulfate has the formula SO4 minus 2, the sulfate anion, and I'm suggesting that you memorize that anion because the ate form of the anion is more common. And once you memorize the formula name of sulfate, you can immediately figure out what the formula is for the sulfite ion, same charge, minus 2, but one less oxygen. So sulfite, SO3 minus 2. And then illustrating that with the phosphate anion, the last example, memorizing PO4 minus 3 is the name and formula of phosphate, then you can immediately figure out that the phosphite anion must be PO3, one less oxygen, but with the same charge of minus 3 as the phosphate anion has.